The National Electrical Code, or NEC, serves as a cornerstone for electrical safety in buildings and homes. It's a comprehensive set of standards and guidelines designed to minimize the risk of electrical hazards. The NEC is not a law itself, but it's widely adopted by states and municipalities, becoming the legal basis for electrical installations. Think of it as a living document, constantly evolving to address new technologies and emerging safety concerns. The NEC is updated every 3 years to reflect advancements in electrical systems and materials. These updates ensure that electrical installations are performed safely and effectively using the latest methods and technologies. Using the NEC involves understanding its structure and how to apply its requirements to specific situations. The NEC is divided into chapters, articles, and sections, each addressing a specific aspect of electrical installations. Firstly, Chapter 1 covers general requirements, including definitions, scope, and rules for electrical installations. This chapter sets the foundation for understanding the rest of the code. Secondly, Chapters 2, 3, and 4 focus on wiring and protection, wiring methods and materials, and equipment for general use. These chapters provide detailed guidance on selecting and installing conductors, cables, raceways, and other electrical components. Thirdly, Chapters 5, 6, and 7 address special occupancies, special equipment, and special conditions. These chapters cover unique electrical requirements for locations such as hazardous locations, healthcare facilities, and swimming pools. Fourthly, Chapter 8 specifically covers communication systems like telephone, radio, and television installations. And fifthly, Chapter 9 contains tables and examples to aid in applying the NEC requirements. These tables provide valuable information on conductor ampacity, conduit fill, and other essential calculations. To effectively use the NEC, it's essential to understand its terminology and definitions. The code defines many electrical terms, and it's crucial to use these terms correctly to avoid misinterpretations. Some key terms include ampacity, which refers to the current carrying capacity of a conductor, overcurrent, which describes a situation where the current exceeds the rated capacity of a component or circuit, and grounding, which provides a path for fault current to return to the source. When applying the NEC, it's important to consider the specific conditions of the electrical installation. This includes the type of occupancy, the environmental conditions, and the available power supply. The NEC provides different requirements for different occupancies, such as residential, commercial, and industrial buildings. It also addresses specific environmental conditions, such as wet locations, hazardous locations, and corrosive environments. One of the most important aspects of the NEC is its focus on overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from damage caused by excessive current. These devices interrupt the flow of current when it exceeds a safe level, preventing overheating, fires, and other hazards. The NEC specifies the required overcurrent protection for different types of circuits and equipment. It also outlines the rules for selecting and installing overcurrent protection devices. Grounding is another critical safety measure addressed by the NEC. Grounding provides a low impedance path for fault current to return to the source, allowing overcurrent protection devices to quickly trip and clear the fault. The NEC specifies the requirements for grounding different types of electrical systems and equipment. It also outlines the rules for installing grounding electrodes, grounding conductors, and bonding jumpers. The NEC also addresses wiring methods and materials. It specifies the types of conductors, cables, and raceways that are permitted for different applications. The NEC also provides rules for installing wiring in a safe and secure manner. This includes requirements for supporting conductors, protecting them from physical damage, and preventing them from coming into contact with flammable materials. In addition to general requirements, the NEC includes specific requirements for special occupancies and equipment. For example, Chapter 5 covers hazardous locations, which are areas where flammable gases, vapors, or dust may be present. The NEC specifies the types of electrical equipment that are permitted in hazardous locations and outlines the safety measures that must be taken to prevent explosions or fires. Chapter 6 addresses special equipment, such as electric signs, swimming pools, and elevators. The NEC provides specific requirements for the electrical installation of this equipment to ensure its safe operation. And finally, Chapter 7 covers special conditions, such as emergency systems, standby power systems, and critical operations power systems. The NEC specifies the requirements for these systems to ensure that they operate reliably during power outages or other emergencies. To stay up to date with the latest NEC requirements, it's important to participate in continuing education courses and workshops. These courses provide valuable information on the latest code changes and how to apply them to real-world situations. It's also helpful to consult with experienced electrical professionals, such as electrical engineers and master electricians. These professionals can provide guidance on complex electrical installations and ensure that they comply with the NEC requirements. Let's delve into specific examples and calculations to illustrate the practical application of the NEC. Consider a scenario where you are installing a new 20-amp circuit in a residential kitchen to serve countertop receptacles. According to NEC Table 310.15b16, for example, which provides the ampacity of conductors, you would typically use 12 per American wire gauge or AUG copper conductors with type THHN insulation, rated for 75 degrees Celsius because it has an ampacity of 20 amps when not subject to dirtying factors. This table is essential for selecting the correct wire size based on the circuit's amperage and the conductor's insulation type. Additionally, NEC Section 210.12 requires arc fault circuit interrupter, or SI, protection for all branch circuits that supply 120 volts, 13 amps, or 20 amps outlets installed in dwelling unit kitchens. This requirement aims to prevent electrical fires caused by arcing faults. Now let's examine conduit fill calculations. Suppose you need to run 3 12 AWG THHN conductors through a 1/2 inch electrical metallic tubing, or EMT conduit. NEC Chapter 9 Table 1 provides the dimensions and cross-sectional area of conductors and conduits. According to Table 4 in Chapter 9, the maximum conduit fill for 3 or more conductors is 40%. To determine if the conductors fit, you need to calculate the total cross-sectional area of the conductors. According to Table 5 in Chapter 9, the cross-sectional area of a 12 AWG THHN conductor is 0.133 square inches. Therefore, the total cross-sectional area for 3 conductors is 3 multiplied by 0.133, which equals 0.399 square inches. Next, you need to determine the allowable fill area for a 1/2 inch EMT conduit. According to Table 4 in Chapter 9, the allowable fill area for 40% fill is 0.122 square inches. Since the total cross-sectional area of the conductors, 0.399 square inches, is less than the allowable fill area, 0.122 square inches, the conductors will fit in the conduit. This calculation ensures that the conduit is not overfilled, which could damage the conductors or make it difficult to pull them through the conduit. Another important aspect of the NEC is voltage drop. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. NEC Section 210.19a on Informational Note Number 1 recommends that the voltage drop on a branch circuit should not exceed 3% at the furthest outlet. To calculate voltage drop, you can use the following formula: voltage drop equals 2 multiplied by K multiplied by I multiplied by L divided by circular mils, where K is the constant for the conductor material, typically 12.9 for copper, I is the current in amps, L is the length of the circuit in feet, and circular mils is the cross-sectional area of the conductor. For example, let's say you have a 120 volt, 15 amp circuit that is 100 feet long and uses 14 AWG copper conductors. According to NEC Chapter 9, Table 8, the circular mils for 14 AWG conductor is 4,110. Using the voltage drop formula, voltage drop equals 2 multiplied by 12.9 multiplied by 15 multiplied by 100 divided by 4,110, which equals 9.4 volts. The percentage voltage drop is calculated as voltage drop divided by source voltage multiplied by 100, which equals 9.4 volts divided by 120 volts multiplied by 100, which equals 7.8%. Since the voltage drop exceeds the recommended 3%, you would need to increase the conductor size to reduce the voltage drop. Grounding electrode systems are vital for electrical safety, and the NEC provides detailed requirements for their installation. According to NEC Section 250.52, a grounding electrode system can consist of various components, including a metal underground water pipe, a ground ring, rod and pipe electrodes, and plate electrodes. The selection of the appropriate grounding electrode depends on site conditions and local requirements. For example, if a metal underground water pipe is used as a grounding electrode, it must be supplemented by an additional electrode, such as a ground rod or ground ring. The grounding electrode must be connected to the building's grounding system using a grounding electrode conductor sized according to NEC Table 250.66. This table provides the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. Proper sizing and installation of the grounding electrode system are critical for ensuring effective fault current protection. Furthermore, understanding the NEC requirements for surge protection is essential for protecting sensitive electronic equipment from voltage surges. NEC Section 230.67 requires surge protection devices, or SPDs, to be installed on services supplying dwelling units. These SPD protect against transient voltage surges caused by lightning strikes or utility switching operations. The NEC specifies the types of SPD that are permitted for different applications and outlines the requirements for their installation. SPD should be installed as close as possible to the service entrance to provide maximum protection. The NEC also addresses the coordination of overcurrent protection devices. Coordination ensures that in the event of a fault, only the overcurrent device closest to the fault will trip, minimizing the impact on the rest of the electrical system. This is typically achieved through selective coordination, where the time current characteristics of the overcurrent devices are carefully selected to ensure that the upstream devices have a longer tripping time than the downstream devices. NEC Section 240.12 provides requirements for selective coordination in critical operations power systems such as those found in hospitals and data centers. Compliance with the NEC is essential for ensuring electrical safety and preventing electrical hazards. The NEC is a complex document, but by understanding its structure, terminology, and requirements, you can effectively apply it to your electrical installations. Continuous learning and consultation with experienced electrical professionals are key to staying up to date with the latest code changes and ensuring that your installations meet the highest safety standards.